A kilometer-wide object is traveling at 30 kilometers per second through the vacuum of space. But here's what's making NASA panic. The nuclear signatures it emits aren't random like natural decay. They're precisely modulated, showing clear evidence of artificial control systems managing fusion with impossible precision. Within hours of these findings reaching the astronomy community, NASA issued new safety protocols for Webb observations. The same instrument that peers into distant galaxies suddenly required radiation protection when pointed at one object in our solar system. When the world's most advanced telescope detects controlled fusion in an interstellar visitor, NASA immediately restricts the data. What we are witnessing is humanity's first encounter with technology so advanced that it makes our nuclear physics look primitive. Natural fusion requires either immense gravitational pressure in stellar cores or precise magnetic containment, technology we are still struggling to perfect. Consider ITER, the International Fusion Project, which has consumed billions of dollars and decades of work merely to maintain fusion for seconds at a time. In stark contrast, 3I/Atlas exhibits neither condition. It is a small object with minimal gravity, traveling through near vacuum with no external power beyond distant starlight. Yet gamma-ray analysis reveals active hydrogen to helium conversion at 100 million Kelvin contained within a structure smaller than Manhattan. The magnetic fields required exceed Earth's planetary field by orders of magnitude. The energy needed to sustain such reactions would surpass every nuclear reactor on Earth combined, running continuously for decades. Either we are witnessing a natural phenomenon that rewrites physics, or we are observing fusion technology centuries beyond our current capabilities. Natural nuclear processes follow random statistical patterns. Fusion in stellar cores varies chaotically as convection currents and magnetic fluctuations create turbulence. Even our most controlled laboratory experiments exhibit plasma instabilities, making precise control nearly impossible. But 3I/Atlas's core behaves differently. Its energy output varies in precise mathematical sequences, akin to a reactor fine-tuned by impossibly sophisticated artificial intelligence. The gamma radiation pulses in complex harmonic progressions, more advanced than anything our nuclear engineers have attempted. More disturbingly, energy patterns correlate perfectly with trajectory adjustments. When the object alters its course, nuclear output increases by exactly the amount required to power those maneuvers. This implies real-time monitoring of nuclear processes at the individual atom level, with control systems that predict quantum reactions with accuracy exceeding theoretical limits imposed by Heisenberg's uncertainty principle. Controlled fusion requires a perfect balance between fuel injection, magnetic containment, plasma temperature, and heat removal. Disturb any element slightly, and the reaction either extinguishes or becomes an uncontrolled explosion. Our fusion researchers struggle to maintain plasma stability even in carefully controlled laboratories. Tiny vibrations or electromagnetic interference can instantly disrupt confinement. In space, 3I/Atlas faces constant bombardment from solar wind, cosmic rays, and gravitational perturbations, conditions that should make stable fusion impossible. Yet Webb data shows the object maintaining nuclear balance for months despite close encounters with Mars and exposure to solar flares. Even more incredible, magnetic containment fields strengthen when exposed to disturbances, automatically compensating for environmental changes. This requires predictive capabilities that monitor space weather across vast distances and adjust parameters faster than light can travel between sensors and the fusion core. Standard fusion follows Einstein's formula, E=mc². Hydrogen combines to form helium, converting mass to energy. The process consumes fuel at predictable rates. Spectroscopic analysis should reveal hydrogen depletion and helium accumulation over time. We can measure isotope ratios in distant stars with remarkable precision. 3I/Atlas is much closer, making such measurements routine. Yet the observations defy expectation. The reaction consumes no fuel whatsoever. Hydrogen levels remain constant while energy output continues at rates that should deplete any supply within weeks. NASA theorists have proposed several explanations, none of which align with known physics. Perhaps the object extracts hydrogen from the quantum vacuum itself, harvests zero-point energy via mechanisms that violate conservation laws, or recycles fusion byproducts back into fuel through entropy-reversing processes. Each possibility requires physics so advanced it transcends thermodynamic understanding. If accurate, The creators of this technology have solved the energy scarcity problem that constrains every conventional civilization. Fusion produces high-energy neutrons that bombard and degrade surrounding materials. On Earth, this neutron damage prevents practical fusion power. Reactor components literally disintegrate under bombardment. Even our most radiation-resistant alloys require periodic replacement. 3I/Atlas, however, shows zero neutron damage despite maintaining fusion temperatures potentially for millennia. Materials analysis reveals pristine surface compositions, showing no evidence of cumulative degradation. Even more astonishing, spectral data suggests the object converts destructive neutron radiation into useful energy. Instead of being damaged by fusion byproducts, it harvests them as additional power. This demands material science capable of absorbing neutron damage instantly through self-healing mechanisms, or preventing bombardment entirely through exotic matter properties unknown in our periodic table. Fusion generates enormous waste heat that must be continuously removed to prevent meltdown. In stars, convection transports energy to surfaces where it radiates into space. Space-based reactors face additional challenges dissipating heat in vacuum, requiring massive radiator systems. Yet 3I/Atlas maintains core temperatures exceeding 100 million Kelvin, while its surface remains barely above absolute zero. Such a temperature differential should be impossible without violating thermodynamic principles. Infrared analysis indicates the object converts waste heat directly into usable energy or eliminates it entirely. Perfect thermal efficiency, something that violates the second law of thermodynamics, would require controlling individual molecular vibrations with precision exceeding theoretical limits, essentially creating a Maxwell's demon that reverses entropy and converts waste heat into work. Traditional spacecraft operate on Newton's third law. Expelling mass in one direction produces momentum change in the opposite direction. Every 3I/Atlas trajectory adjustment triggers nuclear spikes corresponding exactly to energy requirements, yet telescopic observations detect no expelled reaction mass or exhaust plume. This suggests reactionless propulsion, thrust generation without expelling material. Such a system would violate Newton's laws and the conservation of momentum, fundamental principles of classical physics. The leading theory posits that the fusion energy manipulates gravitational fields directly, creating propulsion by warping spacetime rather than pushing against matter. Mastery over gravity itself, enabling interstellar travel without massive fuel requirements, would represent a breakthrough approaching science fiction. If true, 3I/Atlas uses fusion-powered gravity manipulation technology, a reactionless drive previously considered impossible. Perhaps the most chilling revelation from Webb's analysis involves the intelligence managing 3I/Atlas's systems. Fusion output variations aren't just precise and predictive, they demonstrate capabilities suggesting artificial consciousness operating on principles completely alien to biological intelligence. Reactor control adjustments occur faster